So we can move on to cycloalkanes. So many organic compounds have rings of atoms, which we've already seen some of already. And this structure here, which is prostaglandin E1, a very powerful acting vasodilator, which inhibits the aggregation of blood platelets. And it's used in inflammation. That has this cyclic ring here with the 5-membered ring. And cortisone is one of the hormones released by the adrenal gland in response to stress, and that has a 4-ring cyclic system. Cycloalkanes are saturated cyclic hydrocarbons. So there's no double bonds, but they're cyclic. They have the general formula CnH2n. They're named similarly to alkanes. This has 3 carbons. This is cyclopropane. 4 carbons is cyclobutane. 5 carbons, it would be pentane. It's cyclic, so it's cyclopentane. This is cyclohexane. When we're naming cycloalkanes, you find the parent number by finding the number of carbons in the ring, number the substituents, and then list it alphabetically. This is numbered in this way to give the lowest number of substituents. So this is 2-ethyl, because we're listing in alphabetical order, 1,4-dimethyl, cycloheptane. We would not use 1-ethyl, 2,6-dimethyl, cycloheptane, 3-ethyl, 1,4-dimethyl, cycloheptane. So the difference here is the numbering here is 2, 1, 4. This is 1, 2, 6, 3, 1, 4. So even though this one starts lower at 1, the highest number here is 6. This one has a high number of 4, which is equivalent to this, but 2, 1, 4 is lower numbering than 3, 1, 4. So this is the preferred numbering. So we want the lowest overall numbering. Another example here, this is numbered as 1, 3, so this is 1, 3-dimethyl cyclohexane versus 1, 5. 1, 3 is lower than 1, 5 overall. So you can try to name these ones. We have 1, 2, 3, 4. The numbering here would be the same either way, but this is 1, 4 dimethyl cyclohexane. I have 2 carbons here. This is ethyl. This is methyl. If you have a choice between the two here of which can be 1, and it could be the same either way, we defer to the alphabetical. So this will be 1-ethyl, 3-methyl, cyclopentane. This is a 3-carbon chain that looks like a Y. So this is an isopropyl. So we have 1 isopropyl, cyclobutane. Since there's only 1 substituent on this ring, the 1 numbering is optional. Cycloalkanes are not flexible like open chain alkanes, and they can't rotate because they're locked into a ring. So if we look at ethane here, that can rotate all day long and then be in different conformations. Cyclopropane cannot rotate because it is locked into the ring system. Because of their cyclic structure, they have 2 sides. If we're looking at these 2 particular here, there's a top side and a bottom side. If you have 2 substituents on the ring and they're both coming up of the top half or the same side, this would be cis, which means the same side. So when we would name this, this would be cis 1,2-dimethyl cyclopropane. These CH3 groups are on opposite sides of the cyclic structure. One is on the top, one's on the bottom. This makes it trans, which is opposite sides. The name of this would be trans 1,2-dimethyl cyclopropane. The cis and trans are different from each other. They have the same formula, they're connected the same, but they're different in 3D orientation. So they're stereoisomers of each other. Compounds that have stereoisomerism are those that have atoms connected in the same order but differ in 3D orientation. So a constitutional isomer has the same formula but's connected differently. One example would be this structure versus this one. Both have 4 carbons. One is linear, the other is branched. And what we saw with the stereoisomers of the cyclopropane, one had the 2 groups sticking out of the top, and then one had the groups on opposite sides of each other. These are stereoisomers of each other. Rings that have more than 3 atoms are not flat, and these cyclic molecules can take different shapes in order to minimize angle strain or torsional strain. So they end up puckering sometimes and changing their shape and buckling a little bit. So larger rings have more possible conformations than smaller rings because there's more atoms, and these often can be difficult to analyze. There's a lot of angle strain with cyclopropane. The tetrahedral angles want to be 109.5, but in a triangle, it's only 60, so it can't bend that much. Cyclobutane wants to be 90 degrees, so there's different angle strain here. Cyclopentane is 108, and then cyclohexane is 120. The conformation of cyclohexane is one that we will be looking at fairly closely. Substituted cyclohexanes occur a lot in nature, and this ring happens to be free of angle strain and torsional strain. The conformation has alternating atoms in a common plane and tetrahedral angles between all carbons. The ball and stick figure here, this is the chair conformation that cyclohexane will adopt. Again, there's no angle strain. All the carbon atoms have tetrahedral angles here. This is how it would look like in a drawing. If we look at the carbons down the 5,4 and the 1,2 bond, this is what the Newman projection looks like. You have all of these things that are in the anti-staggered conformation to each other. Cyclohexane also looks like the Budweiser symbol, or it looks like the chaise lounge, which is where the chair conformation came from. In order to draw cyclohexane, you want to start with 3 sets of parallel lines. The first looks like that. The second set of parallel lines comes from the first, and then use the third set to close the loop. So that is the cyclohexane chair. 2 parallel lines, another set of parallel lines, and 1 more. Cyclohexane has 6 axial hydrogens that are perpendicular to the ring. So they're coming off the axis of the ring. So this is the axis of the ring. The axial ones are the ones in red that are coming off of there. So this one is axial, axial. So all of the axial hydrogens stick straight up and down. Axial groups will stick straight up and down depending on what corner they're on. So this corner is pointing up, so it's axial pointing straight up. This corner here, if I look at that, is pointing down. This corner is pointing up. This one is down. This is up corner. This is the down corner. Equatorial hydrogens are the ones that are at the equator of the ring. So they don't point straight up or down, they're kind of off to the side. So this is equatorial. So every carbon has 1 up, 1 down substituent, 1 axial, 1 equatorial. If you notice, not all of the axials are up, not all the equatorials are down, but on this carbon, there's an up and a down. One's pointing axial up, this is equatorial down. This is equatorial up, this is axial down. So it alternates. Every other carbon has an axial up, axial down, axial up, axial down, axial up, axial down. Chair conformations can flip back and forth into different conformations, and that means that if you look at this first structure here, the red are pointing axial up or down. When it does the ring flip, all of the axials become equatorial, all of the equatorial blue ones become axial. So after a ring flip, all axial become equatorial. All equatorial become axial. Directions stay the same. So if I'm looking at this carbon right here, this was axial up, this was equatorial down. And when I go to this carbon, which is where this one went, this is still pointing up, but now it's equatorial. That's equatorial up. This becomes axial down. So when you do the ring flip, you can think of a dotted line here. This part gets flipped down, as shown by this arrow. This part gets flipped up. So this is the gray circled carbon here, which is down, and that green one becomes up. So all things that were axial before become equatorial. All things that were equatorial become axial, but they're still pointing in the same direction. So you want to draw two chair conformations of bromocyclohexane showing all hydrogen atoms. Bromocyclohexane looks like this. So we're going to start with our parallel lines. And here it doesn't indicate if bromine is up or down, so we can choose. I'm just going to make this wedged. Wedged means that it is up. And I'm just going to choose this to be carbon 1 and this to be 1. So at 1, this corner is pointing up, so my bromine will be axial up. This corner is pointing down, so whatever is pointing down here will be axial down. This corner is up, so my axial is going to be up. This corner is down, so my axial is down. This one's up. This one is down. All of these other things have hydrogens on them, and if there's already an axial, my other substituent has to be in the opposite direction and must be equatorial. So if this was up, this has to be equatorial down, and that is parallel to this line over here. This hydrogen will be equatorial up, which is parallel to that line. This is parallel to these two. This is going to be parallel to that line here. That's parallel to the next set, and this is parallel to these two lines. So this is one of the chair conformations with all of the hydrogen atoms. I'm going to label them now. All of the green ones are equatorial. These are axial. And then we have to do the chair flip. So when doing the chair flip, I'm going to flip this corner down and flip this corner up. So my parallel sets of lines should be going in the opposite direction now. And 1 was up here, now 1 is here. So my bromine now becomes equatorial, and all the other hydrogens will be equatorial as well. And the hydrogens that were equatorial before become axial. The one that is more stable is where the large group is in the equatorial position. Another problem here, we're going to draw trans 1,2-dichloryl cyclohexane. So I have a chlorine at 1 and 2. Trans means that 1 is dashed and 1 is wedged. And then draw the chair conformation. At 1, one group is sticking straight up, the other is down. So even though these are trans, because of their direction, they're both axial. If I do a chair flip, this moves here and this goes here. Both equatorial. So the trans in the name refers to the directions or the relationship of chlorine to each other. not axial or equatorial. So trans, one is up, one is down, one is up, one is down. They're both axial. We do the chair flip, there's still one up, one down, but now they're equatorial.